How's it going, everyone? Hope everyone's doing okay this afternoon. All right. First of all, are there any questions on anything? I believe I gave you the problems from section 1.4 last time. Okay. Did you have a specific number or general question? Mm-hmm. Oh, for homework is just for yourself to practice, so it's not to turn in. I do hope you keep up with it, though. Okay. So with simple random sampling, the idea is that we just have a large list of individuals that are in the population, and we randomly select individuals from that list. And that's really all there is to it. We know the other processes are generally a little more complicated, although systematic is very straightforward. But simple random sampling says, okay, from a list of individuals, we randomly select however many we need and create our sample. Okay. Now, 15, in an effort to identify whether an advertising company has been effective, marketing firm conducts a nationwide poll by randomly selecting individuals from a list of known users of the product. And so that is simple random, or just random sampling. Because they've got a list of the people that have bought the product, and they want to know what they think about it, so they randomly contact however many people they need from the list to get information from. Now we can contrast that with 19. A survey regarding download time on a certain website is administered via the internet by a market research firm to anyone who would like to take it. So in that case, where people are essentially volunteering to participate as part of the sample, that is where it becomes convenience. In problem 15, because these people have already purchased the product, and we want to know, the company wants to know what people, what led them to find that product prior to purchasing it. That tells them where their advertising might be most effective, so they can learn information from that. And and that's the big thing and I think the example we went over in class, which was our fitness on 22 here. They want to administer a satisfaction survey to its current members. So they randomly select 40 members from his roster and then ask them about their level of satisfaction with the club. So what makes this simple random as opposed to convenience is that they're using all of the people that have paid memberships, and that includes ones that may not be actually attending the club, who may be dissatisfied. If they just gave a survey to people when they walked into the fitness club to work out, that may be more of a convenience sample and it's narrow. So it really depends on how the situation is presented, whether it's going to be convenience or whether it's actually a random sample. So they did randomly select people from the roster, and that's where it becomes random, is that every individual that owns a membership is eligible, and they were randomly selected. They were not volunteering information themselves. Okay. All right. Hopefully that was helpful. Were there other questions before we move on? Okay. So we're going to continue with section 2.1 today and then move into section 2.2 as well. So last time we talked about how we can create graphs for qualitative data. No, I didn't include any definitions in that first part of the lecture because we didn't really have a lot of time at the end of that class where we can spend time on that. So let's continue that here. First of all, we have what's called frequency with a Q. And frequency is the number of times each response appears in the data set. So, if I asked everyone in the class, what is your favorite color? And we came up with green from 6 different people, then green would have a frequency of 6. That's how many times that particular response occurred. Okay? So that's what we mean when we say frequency. Now we also have relative frequency, which is the fraction that represents how often a response is given. Now when we say fraction, that means we could also use decimal or percent, and most of the time we will use decimal. So let me point that out. But the value is based on a fraction or a division, actually. But a fraction that represents the rate at which one answer is selected compared to others. Or that one response is given compared to others, or comparable to others. Let's just leave it at that, the rate that one response is given. So if we said, okay, 6 people picked green as their favorite color, and we have 20 people in the class, then we would take the frequency divided by the sample size. In that case, it would be 6 people out of 20, which means 30% of the class favors the color green in that scenario, or 30%, or 0.3 if as a decimal, however you want to represent that. We just want to make sure we're consistent in a representation. Fractions are usually the one that we don't use because they don't compare well to each other when they're in reduced forms. So typically we use either a decimal or a percent because of those are much more easily compared to each other. When we say fractions, we may have, like, 3/5. How does that compare to 7/10? Well, we could work that one out, and it's not too difficult, but there are other ones that get much worse than that. And so if we want to make an instant comparison, rather than saying 3/5 or 7/10, we would say 0.60 or 0.70. We can clearly see 0.70 is larger than 0.60. Sorry about that. Now I mentioned sample size here, and probably you can discern what that is just from the words that represent that. But just to be completely transparent on that, sample size is the number of individuals selected for the sample that data is collected from. Well, more concisely, we could just say the number of individuals in the sample. Now, how we normally designate these: frequency, we might use the letter F to represent frequency. Relative frequency, we might use RF. And for sample size, we actually use the letter N to represent sample size. Okay. So in that case, we can say relative frequency is the calculation of the frequency divided by the sample size for each response. Okay. Now I want to look at a problem in the book. This is number... what number is this? 14. And this is on page 72. Okay. So in 14, in a national survey conducted by the Centers for Disease Control to determine health risk behaviors among college students, students were asked, how often do you wear a seatbelt while driving a car? Frequencies were as below. First of all, we have the response where students do not drive a car, and that one has a relatively high frequency. We also have ones that never, rarely, sometimes, most of the time, or always wear a seatbelt. So, part A, they want us to construct a relative frequency distribution. Let me go ahead and write down the table on the paper first before we move on. And what I'm going to do is add a column now for relative frequency. I don't know why I drew it out so far, but anyway, yeah. So of our responses, we have no car, and we have the ones that never wear a seatbelt, rarely, sometimes, most of the time, and finally always. And our frequencies are given as follows: 249, 118, 249, okay, 345, 716, and then 3093. All right. So we want to begin by finding the relative frequency. Now, there we go. This is weird. Okay. Now, when we talked about the relative frequency, we said that it would be the frequency divided by the sample size. How are we going to find out how many people participated in this research? What do we have to do to find out the value of the sample size, the value of n in this case? Does anyone see what we have to do there? Right, we'll need to add all the frequencies together, because if these are all the responses that we got, then we should be able to add those together and get a total that represents all the people that responded to this particular question. All right. So 249 plus 118, 249 again, 345, 716, and 3093. So we get a total of 4,770. Alright. I still need the batteries for that calculator. I'm going to turn it off and switch to my less power hungry calculator. So now to get the relative frequency, we just need to take the frequency and then divide by our sample size n, which is 4,770. So that means for the ones that do not have a car or do not drive a car, we'll take 249 and divide it by 4770. And so here, the question is that I get from a lot of students is, how far do we go with this decimal? Because certainly we could go quite a ways if we wanted to. I would recommend 3 or 4 decimal places in most cases, unless we give you a specific number. That's a good place to fall back on. If our data requires us to be more accurate than that, then we will be, but that's only if we have decimal data to begin with. Here, working with whole number data, I would say 3 places after the decimal is just fine, unless it specifically told us to go further. So that's 249 divided by 4770, and so it gives us a relative frequency of 0.052. So we repeat that for the ones that never wear a seatbelt. Now notice we get we get 0.0247. So if we round that to 3 decimal places, what would that be? Yes. So we have a 247, so that because the 7's 5 or larger, we'll round this next number up to a 5. Good. Rarely, 249 is the same as the first one, so we'll just write that number down again. 345 divided by 4770, so we get 0.072, 716, Divide that by the sample size. We get 0.150. And finally, 3093 divided by n, we end up with 0.648. Now, what do you think all these frequencies will add up to? We can kind of see what's going to happen, but ideally, what should it all add up to? One, exactly. Now, this one, depending on how the rounding was done, or how many places we went to, we may not get exactly 1, but that's okay because we know that some rounding occurred. But even with the rounding, it should be very close to 1, if not equal. Okay, so if we add this up, that's 9 and 10 is 19. Carry 1, so that's 6, 7, 8, 29, and then carry 2, plus 1 plus 6 is 9. So yeah, these add up to 0.999, which is approximately 1. If it doesn't add up to 1, it should be within, just a couple of thousandths. I mean, 999 is good. Even if this came out to be 997, that would be acceptable. If it came out to be 97 in the second place, that's way off. Okay, it doesn't sound like it might be way off, but that means if we think of this as a percentage, I mean, this is 5.2%, 2.5%, 5.2%, 7.2%, 15%, 64.8%, and that combines to be 99.5%. Remember, the percentage, we must move the decimal over twice. So this should represent 100% of the people that responded to the question, and because of rounding, it didn't quite equal 100, but it's 99.9%, so we know it's just rounding that is affecting that. So if we're a little bit off, like on this last number, that's fine. If we're off on the second number, that means we have a pretty big problem as far as either how we calculated the numbers or how we added them together, and so on. Yeah, ideally the relative frequency would add up to 1 or 100%, depending on if we're using decimals or percentages. So it should be at or near 1 or 100%. Okay. So when the book says a relative frequency distribution, this is what it means. We make a table where we list out all the responses. We have a list of the frequencies in the second column, and in the third column we'll go ahead and find the relative frequencies. And we'll use this not just for categorical data, but also for quantitative data in the next chapter or section. Okay. All right. Now, we have this information. That was just part A of the question. So that's part A. Part B says what percent of respondents answered always. And we can just read that response from our table. That'd be, we have 0.648, but again, it asks for a percentage. So we'll say 64.8%. We may even choose to round that to 65%, but I think 64.8 is better. That's why I said 3 places after the decimal, because when we look at it as a percentage, we still get 1 place after the decimal on the percentage. Alright, what percentage of respondents answered never or rarely? Now, never or rarely actually represents 2 different responses. So what are we going to have to do with those values? Add them, yes. So for instance, combine them. For rarely, we had 5.2%, and for never, we had 2.5%. And so we add them together, and that will give us 7.7%. Alright, the other thing that we want to do here, there's more questions, but the only one I'm really interested in is creating a relative frequency bar graph. Sorry. So let's see. I probably don't have enough room for that on this page. Okay, so for our relative frequency bar graph, again, we know we go down and across, and we notice that we have 6 different responses that are given. So we'll need on the bottom here 6 places. So we have no car, never, rarely, sometimes, most of the time, and then always. Now again, we want to make sure this is we give this a title and we label the axes. So for this, looking back at this question, this is the research on students who wear seat belts when they drive. So we have seatbelt usage, and specifically this is college students. So we might say seatbelt usage by college students. And to label this axis down here, we'll just say this is the response. And on the left-hand side, we'll use relative frequency. Okay. If we look at our biggest number that we have, that's from always, which was about 65%, 0.65. What can we do there? So I can start making marks in this graph. And when we're working with decimal values or even percentages, what would be and as in particular, if we're looking at our responses over here, which you can't quite see, there we go. What might be a good number to count by on this left axis? I made a bunch of marks there, but what should we count by so that we can make sure to include each of these values? There's actually several correct answers. It just depends on how refined we want our numbers to be. By 5? Yeah, 5 is definitely a good answer here. 5 or 10, yeah. Yeah, 10 is another good option. It just depends, like, we have a lot of room here, so I just made a lot of marks, so we could count by 5 easily. If we counted by 10, that would be fine. We would have to eyeball it a little bit more as far as where these different values are. Okay. So for no car, we had 5.2%, or 0.052, so just a little bit higher than 0.05. Draw a bar there. Never was 0.025, which is actually halfway between 0 and 0.05, so we'll make sure to draw a smaller bar there. Rarely was actually the same as never, so we'll draw an identical bar. Sometimes we had a result of 0.072, so that's about halfway between 5 and 10. Mostly was 15%, or 0.15. We'll go up a little higher for that. And always was about this 0.648, so we'll go up to about 65. Okay. Now, one other thing that we could do here is create a Pareto chart. If we were to create a Pareto chart, which would be the first two responses that we list going across the bottom? Always would be first. What would be second? And then mostly second. Right. Remember the Pareto chart, this is the one where we arrange them in order from highest to lowest. And so we can see always, certainly as the highest relative frequency, as the most responses there. So that would be first, and then mostly is next highest, and then we would put sometimes third. No car and rarely are tied for fourth, so we could actually put those in whatever order we wanted to, and then never would be last because that's the smallest portion of the people surveyed that responded with that answer. So this is a bar graph. Pareto chart, remember, puts the bars in order from high to low. Okay. So that wraps up what we want to do out of section 1. So I would like to move forward to section 2.2. Now, section 2.2, this is on organizing quantitative data. Now, we remember from chapter 1 that quantitative data is broken up into two subcategories. We have what's called discrete, and we have what's called continuous. Discrete means we only have whole number values, so we're just counting things, 1, 2, 3, 4, etc. Whereas continuous means we want all the little fractions and decimals in between, because those are potentially answers. So they're potentially the outcomes of the problem. Okay. So, for discrete first, discrete actually work a lot like the categorical problems. The only difference with discrete is that we do want to maintain an order with them. So with discrete, these will be similar to categorical. But the difference is we always keep our responses in numerical order from low to high. This is, in particular, we use this approach when we only have a limited number of responses for discrete. So maybe we have like 10 or less potential answers to the question. For instance, if we asked everyone how many siblings they had, pretty much we could guess that all the answers would be 10 or less, which would be most of the time, 4 or less. But it depends. But the other answers are possible in that situation on less common cases. So what we would do there is, okay, all the people that say they have 0 siblings, we'd count those. All the ones with 1 sibling, we would count those, 2, 3, 4, etc., and we'd come up with a frequency distribution like we saw in our table from these last couple of problems in the section 2.1. So from there we can make a relative frequency distribution, and we could represent it on our graph using either the frequency or the relative frequency on that left side. Now, the difference now with quantitative data is we no longer use the bar graph, we use what's called a histogram instead. So a histogram is a type of bar graph used for numerical data, quantitative data. With bars adjacent to each other. In this case, adjacent means that the bars are touching each other from one to the next, so they share a common boundary, basically. What else do we have with histogram? I think that's really the only distinction. I already mentioned that we keep the numbers in numerical order, low to high. That's true of a histogram also. That's really all that sets apart the bar graph from the histogram. The histogram is just a special type of bar graph. So, in our textbook, we have this question. This is example 1 on page 76. The manager of a Wendy's fast food restaurant wants to know the typical number of customers who arrive during the lunch hour. The data in the table below represents the number of customers who arrive at Wendy's for 40 randomly selected 15-minute intervals of time during lunch. For example, during one 15-minute interval, 7 customers arrived. Construct a frequency and relative frequency distribution of the data. Okay. I put that down. Sorry about that. Okay. So what we would do here is they've given us, let me put this back on the screen so you can see. They've given us this table of data right here, and they want us to basically count how many times each number occurs. So how many times do 7 people arrive during that 15-minute window? How many times do 6 people arrive? 5, 4, all, everywhere, every number that is used here, basically. Now, on the next page, we see that they've already done this. And I wanted to use this to illustrate kind of the process that we use when we go through the process of working with quantitative data. Now, one method that is recommended here is that, first of all, we write down all the different potential outcomes that we see on the table, and we look at that table again. We see the lowest number given is 1, and the highest number is 11. So we want to make sure we include all the values from 1 to 11. Even if there is a number that's not used, we still want to account for it on our list. And what we do is we go through either by row or by column, and we go through and make a mark on each one of these. Okay, so like the first column is 75262. So we go 7, make a mark, 5, 2, 6, and another mark on 2. And so ultimately this has already been done for each of these columns, and we see the tallies have been created. So we make 1, 2, 3, 4, and then cross on the 5th, and then start the next one. So 1 occurred once, 2 occurred 6 times, 3 occurred once, 4 customers occurred 4 times, and so on. We complete the list that way. Now we notice that there's a little bit of a glare, sorry. We notice that 10 people did not occur at all. So we've just left no tally marks. We'll put a 0 there for the frequency and for its relative frequency. So even though 10 never occurred in this research that was done, it's still between our lowest value and our highest value, so we want to make sure we include it on the graph, the results. Okay, so we have all this information. We got the frequency, and then we know that there's 40 people total here, and we can, because one, we're told that in the beginning of the problem, or sorry, 40 time periods covered. And then we could also add all these together, add the frequencies together. It should also equal 40 that way. So we go through and take each frequency and divide by 40, and then that gives us the relative frequency, and that finishes our chart. Okay. So the question now is creating the histogram for this particular material. Now, if we want to do a frequency histogram or a relative frequency histogram, it's basically the same approach on both. But we did relative before, or sorry, we did relative bar graph before. Let's do a frequency histogram for this one. Okay. Now, on our histogram, we said the lowest number of customers we had was 1, and the highest was 11. And so that'll be what we write going across. This is our number of customers. And as far as the frequency vertical, if we go back to our table, the highest frequency that occurred was 11, so we want to make sure that on our left hand side we go all the way up to 11. And this is just counting by 1. So on this side we have our frequency. Okay. And we also need a title for the histogram. So we go back and we reference the problem for this. So this would be customers arriving at Wendy's during a random 15-minute window. That's kind of wordy. We can just say Wendy's customers. It's a little more concise. It maybe doesn't tell the full story, but at least it references the problem that we're working. Okay, and from here we go ahead and draw our bars based on each frequency. So 1 had a frequency of 1. Okay. 2 had a frequency of, let me bring this a little closer so you can see it. 2 had a frequency of 6. Okay. Now remember, we said for the histogram the bars would be adjacent to each other. So they're sharing this side right here. So wherever this previous one ends, the next one basically uses that same line. I just extended it upward to the next point. So for 3, we have a frequency of 1. 4 had a frequency of 4. 5 occurred 7 times. 6 occurred 11 times. 7 occurred 5 times. 8 occurred twice. 9 twice. 10 did not occur at all, so we'll leave that one empty, and then 11 occurred once. And so this would be our frequency histogram for Wendy's customers during randomly selected 15-minute windows. So 6 had the highest frequency. They had 6 customers, and that occurred 11 times during these 15-minute windows. Does anyone have any questions on that? Now, if we were creating a relative frequency histogram, the difference would be we'd use relative frequency instead of frequency on this left-hand side, and we would change the numbers, but actually the bars would all be the same relative height to where they are now. We just use a percentage or a decimal instead of just the actual number of responses that each one occurred. Okay, so that is qualitative or discrete qualitative data. Now, not all discrete data would fall into that category. Let me show you another example. In this case, all of our data were pretty close together. All of our numbers that we got ranged from 1 to 11, if we go back to the table of results that we had. So it was relatively easy to work with. Let's look at another data set. Yeah, in the case of the histogram, either the frequency or the relative frequency, whichever one we're using in that particular problem, it would always go on the left-hand side. Yeah. Histogram is always vertical, whereas with the bar graphs we said they could potentially be horizontal if we wanted to. But with histograms, it's almost always a vertical graph that we use. Okay, so this data I have, this is actually numbers that I made up, but I have it in my phone because it's nice to refer back to. I know it works out pretty nicely. And the reason I use evening stats classes is I usually have a wider range of ages in there, which makes it a little more interesting, I think. Most of my daytime classes tend to be what we call more traditional age college students, which is 18 through 24, which is fine. I just wanted something with a little more variety. So. Okay. So evening stats classes, these are people that maybe are already working, 9 to 5 jobs, or they're working overnight. In some cases, I've had students that work night jobs that they come to class before they go to work, which I don't know if I could do that, but they do that, so it's good for them. So, anyway, usually these are working people in our nighttime classes, or nowadays, who even knows, but yeah. So I have a selection of 20 individuals here, so we have the ages of these 20 people. Now, if we look at these numbers, we see some 18s, some 19s, 20s, 21, 23, 25, 27, 29, 32, 37, and 45. There's a lot of different numbers there, basically. So we may have 20 people with 12 different ages represented. Now, if we have 20 people, we don't really want to put them in 12 different categories. That really doesn't help us prove anything at that point. So in some cases, even these are actually discrete values. When we think about how people's ages are represented in years, this is a discrete value because now we're just counting, 18, 19, 20, 21, 22, etc. So for continuous values and some discrete values where we have a lot of variety like we do here, rather than put them into individual groups, like for each number, like we could say 18 occurs 4 times, 19 occurs 3 times, and so on. Or, sorry, 18 is 5 times. Anyway, instead of doing that, we might do it by what we call creating groups of groups. We actually call them classes of values, where we have a lower amount and an upper amount for each class. Okay. So for this problem in particular, rather than creating a group for each individual number, we're going to create 6 classes that each cover a different range of values. Create 6 classes of equal width. That's the other part. Now, in order to create our classes, we have to figure out what our class width is. Now, our class width, we define this as the maximum value minus the minimum value divided by number of classes. Now this ends up being pretty involved. When we take our test on this, and you'll see this on the review as well, I will actually create the classes for you so you don't have to find them yourself like we're doing now. Although when we work on the project, you will be expected to create the classes yourself. But the benefit there is you will have your notes to look back on and double check, and you can ask me in that scenario also, just to make sure that you've done it correctly. So don't worry about that too much, is what I'm saying. What is our maximum value in this list of numbers, and what is the minimum at the same time? Our maximum is 45, okay. Our minimum, I guess we can say that is 18, yeah. And we said at the beginning we want to create 6 classes, so I'll divide by 6. Now the number of classes we use ideally will be 10 or less, and it just depends on the data that we have. I went ahead and said 6 because I thought it would be reasonable for this number of people. We could do even as few as 5 or maybe even 4. We don't want to go down as far as 3 because then there's the actual individual classes are actually too large to really discern what's going on with the data. So generally we'd like to stay somewhere between 4 and 10 classes, depending on how much data we have and what kind of values we're looking at. Now, I will always, like for the purposes of what we do here, I will always give you the number of classes to use, or the class width specifically. So you won't have to worry about that yourself, but I'm speaking generally. We would like to stay between 4 and 10 classes. So 45 minus 18, that is 27, I believe. And then 27 divided by 6 is not a whole number. It's 4 and change. 4.5? What is that? Yeah, 4.5. Okay. So we have 4.5, and we don't really want to let our class width be a fraction or a decimal. So we'll round. Misspelled round, sorry. Round up to 5. Now, even if this was 4.3, we would move it up to 5. And the reasoning is that this is exactly the amount we need, 4.5, to get 6 classes. So if we went less than that, we would need more than 6 classes to get that goal. So anytime we round, in this case, with this value, we would always round up. So we'll go to 5 in this case. Okay. Okay. So we'll make a chart with class, frequency, and relative frequency. Now, our first class starts at the minimum value, which is 18 in this case. So we begin at 18. Now, each of our classes is going to cover a range of values. Now, our class width, which we calculated as 5 over here, the way that we use the class width is we actually add it to the 18 here. So our second class will start at 23. Now, if our second class starts at 23, where do you think the first class ends? So that would be 18 to what number? 22. For one thing, we don't want to put 23 there. We don't want the same number, first of all, because if we were to say, okay, we've got a value of 23 on the table, does it go here or does it go here? Well, that's tough to say if the number is part of both classes. So we want each class to be unique and non-overlapping. And that's part of it. The second thing is that when we say class width, it's a little bit misleading. Because most students, when we first talk about class width, they think that's the distance between these two numbers, and that's not the case. Between 18 and 22, that's a distance of 4. The 5 is used between the lower limit of the first class and the lower limit of the second class. And we could also apply it to the upper limit as well. So after 22, add 5. The second class will go from 23 to 27. Okay. But the other reason we say the width is 5 is because if we think of 18 through 22, 18, 19, 20, 21, 22 is 5 numbers. And so that's why the class width is 5, is because there's 5 numbers contained from 18 to 22. Does that make sense? I hope that makes sense. Now, from here, once we establish these first 2 classes, we can get all the other classes from there just by continuing to add 5 to each of these numbers. So add 23 plus 5 gives us 28. 27 plus 5 gives us 32. 28 plus 5 is 33. 32 plus 5 is 37. 33 plus 5 is 38. 37 plus 5 is 42. And then we have 43 and 47. Okay, so we noticed that we did start at our minimum value 18. We did not end at our maximum value. Our maximum value we said was 45. That's the largest value in our set. But we actually ended at 47. Well, the reason for that is it's rare to start and end at the max and the min value specifically. So sometimes there's going to be a little bit of extra space on one side than the other. And that's okay. We usually just start at the minimum, and the maximum will be part of the last class regardless, but it may not be the end point, and that's okay. So it's alright if we don't end right at 45. It goes to 47 because we want these to all be equal width. And that's why we just kept adding 5 all the way down to maintain that width. But it doesn't have to end at 45. Occasionally it will, but it's not required. Okay, I feel like we've reached the end of our time. Let me give you a couple of problems to look at, and we'll go from there. We'll continue this question next time. I'll make sure I save this page and not just toss it in my recycle pile. So for homework, look on page 72. Work on problem 15. And do A, B, C, and D for 15. And also go ahead and make a Pareto chart, which should be capitalized because it's a person's name, I believe. No, for the MyLab or the MyMathLab, whatever you call it now. I don't assign any homework in there because I don't want y'all to. It's not for a grade, but I set that up so that y'all could access your ebook. So you can go in there and look at your ebook, and go to section 2.1 or page 72 and actually find this problem in the ebook. That's why I set it up the way I did. But you can just work it out on your own paper. So that's the only reason I included the MyMathLab, is I know some of y'all bought the ebook instead of the physical copy, which is fine. I just wanted to make sure y'all could access that. That's why I set that up. So, any other questions before we go? All right. Well, you all have a good rest of the day. Oh, one more thing. We don't have class on Monday. So, Monday's a holiday. It's Labor Day. So, because of that, even though we're online, we're not going to have class. So, we'll respect the schedule. Honestly, I could use a day off myself. Anyway, so our next class will be Wednesday of next week, and we'll only meet once next week. So keep that in mind. So hopefully y'all don't have to work too hard. You can enjoy the weekend and take care of yourselves, and I will talk to you next time. Bye.